So good morning, everybody. I am DK Panda from Ohio State University. I know many of you from last 13 years. I think in all the, starting from the very beginning of the OFA or even the OpenIB, when it was formed, I've been coming and sharing some of the things what we have been doing. So this year, once again, like we have some exciting stuff to share. So we have 4 talks here. So today is the first one. We'll be sharing some more. And I know I stand between all of you and the lunch. So I also need to keep that in mind. So this talk will be focusing on mostly on the big data side. As many of you know, like we are in a very exciting phase of the big data. A lot of data is being generated, and a lot of organizations want to operate on that data very quickly and also make a lot of decisions. So this is where we want to take advantage of the latest technologies to see how fast we can try to process this data. So this slide tries to give you a very broad perspective of like where the different components are being used. Let's say if you take any modern multi-tier data center, so you will see in the front end tiers, we have like Memcached D or database like MySQL, HBase are running, and the backend data analytics, which are mostly the offline mode of processing. So there you will see MapReduce, Spark, HDFS are being used. Now, if you take a look at what is the trend of the modern HPC system, so here you will see, most of you know, like we have multi-core processor, high-performance interconnects. InfiniBand has been there for now, 16 and a half years. And of course, the accelerators and co-processors are being used. And also, there is a lot of developments taking place from SSDs, NVMe SSDs. So those are the new things which is coming. And here are some examples of the large-scale systems and how these are being deployed with commodity networking. Even if you see the #1 system in the world in China is actually InfiniBand-based system. So it has gone over the years to that large-scale system. And this might be very common to many of you. This is like summarizing all the different stacks which are being used in the OpenFabrics. Starting from the left is mostly the Ethernet side. And of course, in the right-hand side is the most on the InfiniBand side. And there are a lot of in-betweens with different kinds of performance and features. So especially when I started working, I think many of you might be knowing, 16 years back, we started the MapReduce project, which is the high-performance MPI. That is very steadily going on. I'll talk more about that on the Thursday. And that is also being used in the #1 system in the world, in the China. MapReduce being powering that system. But around 4 years back, we started asking the question, yes, HPC systems with MPI are taking advantage of all these latest technologies. Why can't big data area take advantage of these things? So that's what started to this project. So we asked the question saying, if you have an HPC system or HPC technologies, you name anything, the standard networking technologies, storage technologies, etc., can we actually take advantage of the HPC as such? But before that, we wanted to find out what are the bottlenecks. If you take like a common Hadoop, Spark, Memcached D, etc., what should be the bottleneck? And then can the bottlenecks be alleviated by taking new designs, just like what we have done for MPI? Why can't we do it for big data? And then, so if we can do a good RDMA-enabled design, just like the MPI stacks we had done, then what kind of benefits we'll be able to get? And also not just the network, but can we take advantage of like parallel file system? If you have a Lustre, can you directly run these kind of stacks from Lustre itself? And then how much benefits will be there? So broadly, we wanted to bring HPC and big data together. So that was the whole goal of the project, trying to see that can they be convergent. And if you have an HPC system already deployed, let's say you have a HPC cluster, in addition to running your MPI jobs, can you run Hadoop jobs? Can you run Spark jobs? And all of them can coexist. And then your users don't have to deploy a separate Hadoop cluster or a Spark cluster. So that is the kind of the big motivation. And I'll show you how we have been evolving on those solutions. So to do that, we tried to first come up with the overall design challenges kind of thing. So here, if you see like at the bottom, you will see like the multi-core, many-core architectures or different kinds of networking technologies, storage technologies are there. And then, of course, at the top, we have the different kinds of applications and benchmarks. So how do we bridge the performance features of the lower layer to the upper layer? So now if you take a look from the top, all these big data applications typically use these middlewares, let's say HDFS, MapReduce, HBase, Spark, or Memcached D. And most of the time, if you go inside, you will see they've been using sockets. Okay, so that is the first thing we try to analyze. And as many of you know, sockets have good features, portability, but performance-wise, that is not the best option. So we try to come up with a set of communication library components here, like how to handle point-to-point communication, let's say threaded model, virtualization, I/O file system kind of things. It's a roadmap. We started like 4 years back, and we have made progress on some of these components. But to get the best performance, first we ask the question saying, can those sockets be modified to something else? Okay, that's the lowest level. If we can go to the network, we'll get good performance, and that's what we did in the MPI stack. Like if you go back like 16 years back, the MPIs were all running over sockets. Then we wanted to take it to the InfiniBand burst kind of things. So similar kind of things we wanted to do. But then that was like a phase 1. But then the phase 2 is like, if you can make the networking layer fast, most of these stacks, now you can explore the upper level also enhancements, because these stacks were designed with slow network in mind. So now if we can enhance the networking stack, so we should be able to go and make changes to the upper layer and we can get more benefits. So these are the kind of 2 phases we have been working on, and I'll try to show you some of the detailed designs and performance later on. So we started the very basic questions to start with. This was like 4 years back, saying if you take a look at very simple form, like your big data applications running over sockets, running over GIGI, Ethernet, or even InfiniBand with IP over IB, they can run. But can we make into a right-hand side design, so where we can bring things running over verbs, natively over verbs? So that was the first problem we tried to solve. So if we can make it run over verbs, then the designs can be moved to InfiniBand, or it can be to Rocky, iWarp, or any of those in the OpenFabrics stack. So that is the kind of things we have been continuing. So not only like we have done the research, but just like our MPI project, we have started this new project. Some of you might be familiar, called High Performance Big Data, HIVD. So we are bringing both the HPC solutions and the big data solutions together. And these solutions are now available, just like the MPI library, MapReduce library, these are available. If you go to that HIVD site, you should be able to download these libraries. We have RDMA for Apache Spark, RDMA for Apache Hadoop 2.x series. And here also in the Apache Hadoop, not only we have the integrated version, we also have plugin versions. Because in this community, many people run like the Cloudera stack or Hortonworks stacks. So in this case, you don't have to replace those stacks. We have plugin designs, so you should just be able to install our plugin, and that should help you to get all the benefits what we have done in the new designs. Similar kind of things we have done for the Apache HBase, Memcached D. Of course, Hadoop 1.x we have, but that I think gradually being phased out. We are not maintaining it anymore. And in addition to those, just like those of you are familiar with our MPI libraries, not only we have the basic MapReduce library, but also we have a OSU micro benchmarks for MPI. Many of you might be familiar. The same thing we have done here. So we have a HIVD benchmarks, so we call it like a OHB. So I'll also talk a little bit about that. So you should be able to download and evaluate different stacks, evaluate different components, just like the same idea of the OSU MPI micro benchmarks. So these stacks are gaining momentum. So far, like there are around 215 organizations from 29 countries are using. We just crossed we're coming very close to 21,000 downloads from our site. People using this kind of stack. So if you want to try any of those things, just please go to that hivd.csc.ohio-state.edu. And the stacks currently run on InfiniBand and Rocky. So if you have any InfiniBand deployment or Rocky deployment, they should directly work. So let me then go into a little bit more details on these designs or the releases. So this is like our Hadoop 2.x distribution. So it's not only like we started with RDMA design, but as I said, like these are 2 phases. We have done the designs. So now you can see that within the Hadoop, we have made enhancements to HDFS, MapReduce, to RPC. We also have we have also very good integration with Lustre. The next slide actually will talk a little bit more. And I talked also about plugin-based design. So the latest release is based on Apache Hadoop 2.73. Yesterday night, 2.8 was announced, so we'll gradually update to that. We are also working on the Hadoop 3.0 stack, which was announced earlier. Now, the one thing I just want to make sure that this is compliant with the Hadoop version. So if any application or your ecosystem running, let's say on Hadoop 2.73, our stack will run with that. There are no changes needed, so we keep the APIs the same. We don't break any of the APIs. So it just gives you more performance and scalability. So this one actually picture shows the overall stack. So you can see like there are different components here. The storage, the HDFS layer. So we have like a in-memory designs for the HDFS. We also have heterogeneous storage, Lustre integration. We also have a burst buffer. For the timing, we use the Memcached D as a burst buffer. But if you have real hardware-based NVMe, those kind of things, we should be able to also link with that. And then the RDMA enhanced RPC is there. And also in the MapReduce side, the same thing we have done, like the taking advantage of the RDMA and in-memory processing. So the MapReduce has been enhanced. And the most important thing, if you see on the left-hand side, so we provide very nice integration to the existing job scheduler. So that is the whole idea. Like if you have an HPC cluster which is using Slurm or using PBS, so we also have the hookups. So they will just run just like any other additional MPI job. So you don't have to do any changes. Then Spark kind of things, so similar kind of things we have done. In fact, just 2 days back, we made the latest release. So this is based on the Apache Spark latest 2.1.0. So that also is the same thing, high performance RDMA-based designs. So here again, this is like the RDMA-based data shuffle. We have some SCADA-based shuffle design and also some good buffer management, non-blocking designs. And once again, this is compliant with this 2.1 release. Now, in addition to you trying to download from our stacks or our library, these are also installed. Those of you are familiar with like US universities, like the NSF has the Exceed environment. So we work very closely with San Diego Supercomputing Center. So their SDSC, the Comet system has already installed this. Similar thing about the Chameleon Cloud. So if you have any accounts on these kind of systems, in fact, you don't have to do even any installation. So these are already available. Just like you submit the jobs, your MPI jobs and all, you should be able to submit your Hadoop and Spark jobs. Now, same thing we have done with HBase. That is the component. Of course, HBase sits on top of the basic HDFS and MapReduce. So that can take advantage of all the designs. But we have also explicitly gone and made the HBase itself RDMA enhanced. Similar kinds of features and all we see. And then is the Memcached D. So that is the kind of the component which gets used in a lot of Web 2.0 environment, trying to combine a lot of memories from the nodes. But we have gone one step further. It is not just the memory. We can also combine the SSDs on the nodes. So it is a hybrid memory design. So you can have a very large capacity of the Memcached D. So that's why we have designs with SSD-assisted hybrid memory. And in addition to that, we have also changed to non-blocking APIs. I'll talk about that a little bit later. And again, the latest release is based on these ones. So then the micro benchmarks I discussed earlier, just like the MPI micro benchmarks, if you see like here we have introduced the HIVD micro benchmarks. Those of you who are working in these areas, you will see that there are not many really low-level benchmarks. People always run sort, TeraSort, those kind of things. I'll also try to show those numbers. But let's say you are trying to evaluate HDFS itself or MapReduce itself. How do you evaluate and compare? So this is where like we are trying to contribute, coming up with like let's say micro benchmarks here, purely HDFS. So irrespective of any other components, you should be able to go and evaluate or compare different HDFS stacks. So we have introduced these micro benchmarks. Similarly, we have done for Memcached D, HBase. So this is again, these benchmarks are available from our site. Now to illustrate this point, as I was telling, let me go through some animation and then just to hit the point that what we are trying to achieve is the exactly same like on the HPC cluster, on existing HPC cluster, you should be able to run these jobs. Okay? So for example, if you have a cluster with different kinds of physical resources and resource managers like say Slurm or Turk, now of course you can run not only the basic MPI jobs, you can run Hadoop jobs, Spark jobs, MPI jobs. So it's just like your users, they are simultaneously working on the same system. Okay? And so here, for example, somebody wants to do the Hadoop job. I discussed about all these things. You can have different kinds of configuration of the file system, like the HDFS HHH. You can use RDMA MapReduce. You can configure it in different manner. You can tune it based on your jobs, characteristics, kind of things. So just like any MPI stack, we have a set of runtime parameters also, and there is a default set of parameters. And same thing, you can also do Spark. So the idea is that if you already have an access to an HPC cluster or deployed something, you don't have to do anything differently for running these kind of jobs. So that is the kind of the message I want to give. So with that kind of a background, let me go into a little bit more details, and then we may not have time to talk all the detailed designs. I'll try to introduce some basic designs, and then or just illustrate saying how we went about those designs and what kind of benefits you can get, and then we have some advanced designs. So the HDFS design, as I said, like we started, this was our first component, because if you know, like the Hadoop, HDFS is the layer where you spend most of the time. So this was the first paper we presented at Supercomputing 2012. So the idea was that most of the time in the HDFS is the replication takes the most amount of time. So that is the part which we wanted to enhance. So here you will see that the HDFS write, we made a hook to the JNI interface directly running over the verbs instead of running over the sockets, and we wanted to focus on only the critical part, so that if some other calls are not critical, they still go over the basic Java sockets interface with IP over IP, those kind of things. So we didn't want to blindly go and change all the calls. It is where, like, the architecture make the common case fast. That's what was our objective. To do it. So that is our first design. Then we went into the second level design that was like presented at HPDC. And then the third design, we tried to brought it here. So this was like the heterogeneous storage we wanted to handle, which can take like hard disk, SSDs, RAM disk, even the Lustre, because different HPC cluster can have different configurations. As you know, some of them have local disk, some of them need not have local disk. So we tried to provide a unified design so that you can actually configure it. Based on your system configuration, you can say, okay, this much data sits on the Lustre, this much data sits on your hard disk or SSDs, or even if you don't have anything, everything can run over Lustre. So it provides you a different kinds of flexibility to configure the stack for your existing cluster. And then, of course, with that kind of heterogeneous storage design, we also provided different kinds of data placement policies, hybrid replications, etc. So then we tried to do on the MapReduce, the similar kind of things. You will see it is not just the MapReduce communication. We wanted to take it through the verbs, but we also introduced RDMA-based shuffle, different kinds of prefetching and caching map output, in-memory merge. Then as you can think, just like the MapReduce, if you think of an application or an algorithm, the question is how best we can exploit the overlap. If you can exploit the overlap from different components, you will get better speed up. That's what we tried to do. We tried to introduce some advanced overlapping between the map phase, shuffle phase, merge phase, and reduce phase, so that your MapReduce jobs runs much more faster. So now those kind of like a little bit of background design. Now let's see what kind of benefits you can see. So here what I'm trying to show in some of the slides, you will see a yellow bar and the red bar. So both are running on the same hardware. This is like the same InfiniBand. In this case, it is an InfiniBand EDR environment. So this is the random writer. This is the TeraGen. These are the standard benchmarks in the Hadoop field. So what is happening? The same thing is running over the yellow bar is over IP over IP, whereas the red one is our new design, which is running over verbs. So with exactly the same hardware, our software stack is able to give you benefits here if you see like a factor of 3 or factor of 4. Okay? So no difference to the hardware. We are trying to, because we are able to go, just like a high performance MPI stack, we are able to go into the bottom of the network. We are able to get this kind of improvements. So then these are some additional numbers like a sort and terasort. You can see here again, like this is a 61% benefit. Here it is an 18% benefit. Now, of course, the Spark can also run over HDFS. And one of the projects which is continuing also in the Spark community is called Tachyon. So here we are comparing the Spark applications. This is from the HDFS Garden. We are comparing our Triple H design versus Tachyon, which has been renamed as Aluxio. So here you will see, compared to the IP over IP design or Tachyon design, we are able to provide, like the left-hand side is Teragen. We are able to improve by 2.4x, and the right-hand side is TeraShort. We are able to reduce the time by 25%. Now, moving forward, if we take a look at the Spark, we took a very similar kind of design. So this was proposed like around 2 years back. So if you go to the internals of the Spark architecture, so here you will see like there are different kinds of server and client components, NetE server, NetE client, NIO server. So we introduced an RDMA server and RDMA client. So that can actually directly go into this RDMA-based communication. So then, of course, in addition to these basic components, we had to handle the efficient connection management, some non-blocking data transfer of JVM, heap buffer management, etc. So now if you take a look at, again, these numbers are from HDFS Comet. Some of the common benchmarks in the Spark are like group by, sort by. So here, if you see, this is running over 1,500 plus cores. And once again, the same thing, the hardware is exactly the same. But with the RDMA design, this is for like a sort by test, we are able to reduce the time by 80%. So that means we are making it 5 times faster than what is running over IP over IP. And the right-hand side is also similar kind of things we see with a group by test. So then these are some numbers with HiBench. So this is the Intel HiBench, which has been introduced to evaluate some of these stacks. Here also we see same thing, like this is a page rank, that is a component of the HiBench. Here we see like a 37% performance improvement with a gigantic data set. So there are like a huge big data, gigantic data sets. And here also we see on the right-hand side, similar kind of thing, 43% benefit. Hardware being the same, but just the software stack with the RDMA-based design is able to give you this benefit. So then these are some application-based numbers. So we are working with some of the real application scientists who are using the San Diego Supercomputing Center. So this is a Kira toolkit. So this is the Big DL, the distributed deep learning toolkit, which is using the Apache Spark. So here you will see like we get 21% benefit. This was very interesting. Just recently we got these numbers. So if you see even this Big DL, see the yellow lines, as we are increasing the number of nodes, even the basic IP over IP design, the Spark design doesn't even scale the time. So it is not like a scaling, whereas our red lines, you see steadily is able to scale with increase in system size. With a 384 cores, we are able to give you benefits in the end execution time by almost closer to 4.58x. Okay. So let me just move ahead. These are some of the numbers again with Memcached D. That is the other component which I introduced earlier. So these numbers were taken on the TAC here in the Austin. That is the largest InfiniBand cluster. This is the FDR interconnect. So here you will see, like as we increase the message size, just for the latency, we are able to improve by a factor of 20. Okay, the Memcached D latency. And we try to scale the number of clients. And here we see like almost factor of 2 improvement in terms of throughput. So with the same hardware, we are able to give, those of you who might be familiar with Memcached design, to the end application or the clients, we can give significant reduction in latency and a big collective throughput gain. So that helps the different kinds of the ISP providers to utilize the same hardware but to get better benefits. Then we have done some more like different kinds of online data processing workloads. So here it shows like a read, cache, read kind of things. You get reduced by 66%. The latency, you can improve the throughput by 69%. So while these are some of the basic designs, we are also looking forward to the next level of designs, which are like advanced designs I introduced earlier. So one is, I want to show 2 of these things. One is a Memcached D with hybrid memory and non-blocking APIs. So the idea here is that most of the Memcached D designs are trying to focus just taking aggregated memory from a set of nodes. Okay, so that itself is good. It will allow you to have a good amount of memory. But people are also considering, because SSDs are also fast and most of the nodes come with SSDs, so you can combine memory together with SSDs. Okay, So this design is very similar to, let's say, processor architecture. You can say L1 cache, L2 cache, L3 cache. So here we can say this is the first level memory, the second level memory. But the idea is that when data does not fit into the memory, it should not lead to a big penalty. Okay, so that is the whole idea. And here we have done a very detailed design analysis kind of things, different. The left-hand side is the data fits in memory, right-hand side data does not fit in memory. And then with the different kinds of our designs, not only IP over IB, RDMA, with SATA, with hybrid NVMe, where we are able to show that our new designs are able to give you a very big capacity for Memcached D, but with very little degradation in the performance. So we are able to show improvement by 5x here, and then when data does not fit in memory, we are still able to give you benefits of 2 and 2.5x. So then last year, we went one step further. In addition to the hybrid memory, when we tried to analyze the Memcached D stack, we saw that all these calls are blocking. So those of you who are familiar with MPI, you might have seen, we have gone through the same path in the past. All the calls were earlier blocking, like MPI send, MPI bcast. Over the years, they have been changed to non-blocking. So MPI I send, MPI I bcast, so that you can initiate those operations, and while the communication is going on, you can compute. So same idea as we brought to Memcached D, so that we can have the Memcached D APIs, instead of being blocking, we can make them to non-blocking, and that again gives very big benefits. So that is our new design, so that we can see here like some 16x latency improvement, 2.5x throughput improvement when data does not fit in memory. When data fits in memory, we also see similar kind of benefits. So then finally, we are trying to go one step further, trying to accelerate the I/O aspect, not just the communication aspect, but the I/O aspect. So here we have introduced a new design. We call it burst buffer over Lustre for accelerating big data I/O, or BOLDIO. So the idea is that if you have a Lustre, then we have a burst buffer Memcached D environment, and we can utilize that to reduce the I/O overhead, the end I/O overhead when the data going back and forth. So here we can have like the same non-blocking Memcached D APIs or client-based application. These are some of the techniques we have used to cut down on the I/O time. And this is a very dense slide, but we have done a very exhaustive comparison with all the different kinds of designs which are available outside. So this is the DFS I/O throughput. This is the Hadoop Spark workload for different kinds of benchmarks. The Lustre Direct versus even we have compared also with the Alexio, remote, local, and this is the BOLDIO, which is the green. So you can see for different kinds of write and read, we can give you benefits, factor of 3x or 7x. Here we are able to reduce time by 21% kind of things. So these are some of the advanced designs which are coming out. So just to conclude, these are some of our ongoing work. So as I indicated, all the HIVD releases are there. You are welcome to start using them. We are continuously, just like our MPI project, we continuously also monitor all the latest developments taking place in the Hadoop and Spark. So periodically we take our new designs and integrate with those public versions. So we'll have the new designs coming. Of course, many of you must be knowing there is also the field is moving into the next phase, which is the streaming data, not just like the batch data kind of thing. So we have already started working on some of those things, how to accelerate those kind of streaming operations. We also have a component which is like a MapReduce advisor, because nowadays, as you see, the clusters are very heterogeneous. So even if we set some default configuration, they may not be the best. So can some component automatically find out all the different parameters? It's just like tuning an MPI library. So here we are having tuning of the Hadoop stack. We are also looking at the Impala. And then we also look forward to the MapReduce, introducing more benchmarks, MapReduce, RPC, etc., and some of the new advanced designs. So to conclude here, what I briefly introduced, discuss some of the challenges in accelerating the big data middleware, presented some of the initial designs, and the results are promising. But of course, the field is moving so fast. Every few months, you see some new stack have come in this field. So we are trying to monitor that very closely and then see how to take the latest advancements of the HPC technologies to accelerate those. And if we can do that, my hope is that we'll be able to really enable the big data community to take advantage of the HPC environment so that they can be actually combined together. That's the kind of convergence I mentioned earlier. So in this direction again, I'm looking forward to collaboration with this community. If you have used these stacks or if you want to use the stack, we'll be happy to have a further discussion and then see whether it really helps your end applications or not. So these are just a quick thing about the 3 additional presentations. Thursday, I'll talk about the MPI project, and also we have done a lot of work on virtualization to bring together with SRIV, those kind of things. And then on Friday, we'll be talking more onto the NVM aspects of this, so how you can accelerate the big data things with NVM or stuff. So to close, these are our standard, I just want to thank all our sponsors, but more importantly, these are all my heroes. Okay, these projects in this community, we have been working for 16 years. So I want to always, I just come give the talk, but these people do all the hard work. Interestingly, today I have 4 of the students here, or the staff. Can you please rise? I think Santhan, Washir, Nusrat, Ranjit. Okay, so these are, give a big hands to them. So they do all the hard work. Okay. So at the same time, we are also trying to move another direction here. I just want to indicate this is a new workshop series we have started together with the academic conference. It is one called High Performance Big Data Computing, HPBDC. We have been doing with IPDPS. That's the Major Parallel Processing Conference. So this will be held in Orlando. So we have a very nice set of papers, as well as Satoshi from Japan will be giving the keynote talk. We have a very interesting panels and also a lot of interesting papers. So please go to this site if you plan to attend IPDPS. I welcome to join this session also. So we want to raise the awareness in the community, saying how to bring HPC and big data together. So with this, let me close here, and I'll be happy to take few questions.